Wow, this is a very, very late start to Astronomy Daily Live. So, hey, everybody! This is attempt number 2 to get this going here. It looks like it's going. It looks like it's going. Yes, it most definitely does. That's better. That's better. So, come on in, friends. Sorry about sorry about that. Those kinds of things are going to happen from time to time. Such is life. Such is life. So, welcome. Welcome to Astronomy Daily Live. I'm going to send out my Hangout link to Bobby. The only thing that I did differently that I've never done before is that I sent the invite from the little Hangout screen that I have. Whoop. Um, it's the only thing that I did differently this time. So I don't know if that messed things up. All right, Bobby, I just sent you the link. And I need to go over there and grab the chat. Astronomy Daily Live, usually starting at 2 hours UTC. It's now 2:13. Can you believe this? Got to go grab the chat. So hope everybody's doing well. Thanks for putting up with mild difficulties here, but that's how it goes sometimes. This is a very, very casual, fun live stream. We're not too picky here. You know, let things slide a little bit. It's all right. Okay. So now let me go back over to that. And then I'll pop back over to the chat. And I don't see any chatters yet, but I probably will. I see that I have viewers. Hey, and there's Bobby. Nice to see you, Bobby. Let me put on my headphones here. All right, there we go. I'm going to turn you down. Turn you down a little bit. Think about there. Okay. So, cool. Well, sorry for being a little bit late. That's how it goes. I started up the live stream on time, and I was just talking away like I normally do here, and just sort of waiting for the room to fill, and it's like, where is everybody? And not not that I expect you all to come in here, right? You can do what you want, but usually there are a few who pop in, and it's like, what's going on? And I didn't see anybody in the chat, and so it's like, oh, okay. So I just did a restart. So hopefully that wasn't too confusing to anybody. So no big deal. No big deal. So I posted a couple of pictures over on the Discord server, which I would like to share with you. So we're talking astronomy here. This is all astronomy. We'll mix in some science and you know sometimes some tangents, but usually not too far off of a tangent. Now, I think the first one that I do here, I was uh, looking up some interesting things about M104 and just clicking around and all that, and saw this interesting object. It's called Hoag's object, and it's like a ring galaxy. And so I'm like, oh, I'll go over and grab the raw HST images and see what it looks like. And so that's all I did. I just grabbed um, three different images at three different wavelengths, and I said, okay, image one is going to be this, and image two is going to be this color, and image three is going to be a third color. And I just used, as you can sort of see here, red, green, and blue. Right, that's all I did. So everything on here that is sort of red, green, and blue streaks of some sort, those are cosmic rays. Those are um, uh, very, very, very fast moving particles that come from uh, everywhere. We really don't have a good explanation as to why they're there, but CCD cameras pick these up really, really easily. And these exposures are pretty long. I think they're on a range of like 1,000 seconds. So that's that is quite a long time. And so over the course of those exposure times, you're going to get a lot of cosmic rays. So that's what this is. This is sort of it's calibrated data, but it's raw, right? I mean, it hasn't been cleaned up um, or massaged in any way. And I just did a simple um, red, green, blue thing, and I think I played with the brightness and contrast a little bit to make sure that the background was nice and dark, and that the ring and everything sort of popped out. As you can see, these, it's kind of hard to see here, um, but you see these little white spots in here, all these around here. Those are very, very likely to be globular clusters that are associated with that galaxy. And so that's just kind of cool. Um, so yeah, I mean, that's like uh, that's a pretty good circle. you know, that's not bad. That's not bad.
And like how long is those exposures?
I think they were around like 1,000 seconds or so. They varied them depending on what wavelength they were looking at, but yeah, I want to say like around 1,000 seconds or so each. Yeah. So that's this is pretty true color. The red one I think was like 815 nanometers, which is very, very red. Um, the green one was I think around like 600 nanometers, which is pretty green. And then the blue one I think was like 450 nanometers, which is very, very blue. You know, that's almost ultraviolet. So you know, this really isn't a true color image, but it's a pretty amazing object. The One of the interesting things about um, this particular image, and I don't know if you noticed this or not yet, but behind this galaxy, right? You've got this main ring galaxy, you know, this face-on ring. Well, looking through the ring, there's another ring galaxy behind it. So um, uh, that's an incredible coincidence. Um, and you know, I say that this is behind it, just based on the fact that it's smaller, right? So it's probably further away, probably. So it's probably behind it. Whether that's true or not, can't really tell from a picture. There's no way to do that. You've got to look at these things spectroscopically to see how they're moving. Um, yeah, yeah. But it's a pretty galaxy, pretty amazing.
And what's this galaxy called again?
It's called Hoag's Galaxy. Hoag. Hoag's Galaxy. And it's just a ring galaxy, but I think it's spectacular. You know, I'd like to try to clean up the images so you know you don't have all this mess. But that was actually done. So let's go over. We can take a look
Hey,
at
what's
that.
up, Jills?
Hey there, Gilles. Nice to see you in the chat. So Hoag's object. So here we go. These are. I'm pretty certain that this is the same data. It's just been cleaned up. So it just looks a little nicer. And as you can see, you know, this is flipped. So this I think they orient correctly, such this is north and this way is east. But as you can see in this case, you know, this galaxy is up there. So it's been flipped 180 degrees, but cleaned up a lot too. So, you know, able to bring out a lot of detail, probably use slightly different colors to make this, but quite an amazing object. It's sort of like um, an elliptical galaxy in the middle with
Can
this
Auto find that galaxy
ring.
today?
What's that?
Can Auto find that galaxy today?
Oh, you know what? I think, Atta, that this is pretty faint. If you'd be able to see anything at all, you would probably just see the middle part. You probably wouldn't see that. Um, Probably not. But let's see if it let's see if just Wikipedia gives a visual magnitude. Ooh, 16.2. No, to see with your eyeballs to be able to see a 16.2 magnitude object, you need about a half-meter telescope or so. So, yeah.
So
An
she
8
can
inch,
see the nucleus but not the ring.
yeah, I don't think you're going to see anything. At 16.2, that's sort of um, the magnitude of the entire thing. So it's actually going to even appear fainter than that. So yeah, no chance of of us being able to see this. Now, if you were to do a long exposure, right? Um, Now the HST, right? This image is, as I said, about 1,000-second exposure, but that's a 2.3-meter telescope. So um, you could probably do about as good with I don't know, maybe like a half-hour exposure or an hour. Let's actually go over. Let's follow our noses here, and let's see if anyone over at Cloudy Nights has ever posted some um, some images of Hoag's object. Let's see. Oh, it looks like I got to sign in. Not quite sure why I have to do that, but I will comply. Dun, 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 dun. Okay, so I think if I go here, not quite sure how to search. Let's see if there's a search thing on the. Yeah. So for those of you who don't know about Cloudy Nights, this is a absolutely fantastic um, forum, um, mainly for the amateurs. But these people in here are pretty intense. Let's see if there's anything. There's got to be. Uh, let's see what this one shows. Da-da-da. Oh, I went down too far. I don't see any pictures here. Okay, so we're gonna skip that one. Hey there, Patrick. Nice to see you in the chat. Let's see. Is this one of them? It probably has a bunch of different names. Most objects do. There we go. Okay. So that's what it looks like. What has he got? He's got a 14-inch. So he did two 10-minute exposures in red, green, and blue, and then a luminance exposure, 4 of those 10 minutes long. Let's look at the full image here, supposedly. Okay, so wow, there's a bunch of galaxies around there. But there's Hoag's object right there. So as you can see, the difference between Hubble and a 14-inch, there you go. There's the difference. Looks like it's in maybe some kind of a group of galaxies here. That's pretty cool. So that's that's a pretty long exposure thing, right? You're doing 20 minutes on 3 colors, so that's an hour right there. and then another 40 minutes, so an hour and 40 minutes of time went into getting that image. So, but pretty cool though, anyway. Hoag's object. It looks a lot more filled in here, but it's starting to darken, right? It's pretty uniform and flat, and then it darkens, and then you have the central thing, and then it darkens again, and so you can definitely tell there's something going on in the middle, but yeah, it definitely doesn't really look like that. Pretty cool. These galaxies are pretty cool looking too. Whoop.
Interesting.
Nice image. Pretty nice image. These long exposure images, what you're looking for is make sure that the stars are nice and round. That's the most important thing.
It's pretty interesting when an object's around with a group of galaxies, it makes it real good.
Yeah, yeah. It looks like it's in a neighborhood of sorts. Not quite sure. Don't don't know much about this particular object. They say it's like 600 million light years away, so that's pretty far. That's pretty far, and that's why it's so faint, right? Because it's just it's pretty far away. It's also look like looks like it's pretty big too, 121,000 light years across. That's comparable to the size of what we think our galaxy is. But it's a pretty one. But yeah, 612.8 million light years. So yeah, that's pretty far. Pretty far. And that's why it's so small, and that's why it's so faint.
And how far is this object from the Earth?
Like 613 million light years. So yeah, that's pretty far. That's pretty far. My guess is based on that these galaxies here, all of them, maybe not all of them, but at least the larger ones here are probably in the foreground. This is probably behind them all, because that's pretty darn far. These are probably closer. So let's see, what else? Is there anything else interesting about this guy? Yeah, of course, they have no idea how it formed. Um, the only thing, at least imaginable at this point is some kind of a collision. But yeah, I don't know. Such an event would have happened at least 2 to 3 billion years in the past. So yeah, pretty cool. So that was one thing that I posted over there, and then the other thing that I posted over there was just some pictures of yours truly back in the day. Where did I do that? Did I do that here? When I was going up to, yeah, here it is. When I was going up to the 61-inch pretty much every month or so. So this is circa like 1992 or so. And so there I am And I was, I think I was like 22 or 23. So yeah, pretty funny. Um, this whole platform on the bottom here, whole thing I'm standing on, uh, went um, down and up, right? Uh, I had to put um, some instrumentation onto the back of this thing, and so instead of having to lift it up on there, try to hold it and bolt it on, you would just use the platform to raise everything up to the telescope. Pretty typical.
Is that still functional today?
Yes, this telescope is now being very very used. Um, I think it's um, one of the, well, I mean, it's still doing science, but it's one of the telescopes that the Catalina Sky Survey folks use as a follow-up telescope. So they have telescopes to um, discover these asteroids, but then they need to be able to follow up on it, measure the magnitude, position, all that stuff. So this scope um, is used in part for that.
Sounds great.
Yeah. So all the way across here, right? All the way across here is 61 inches, right? That's the main mirror. Then they had a couple of finder scopes, these big refractors. They had balances, all that kind of stuff. As you can see, this mount um, doesn't allow it to point due north, right? I think it can only go up to like a declination of, oh, I want to say like 65 degrees north, something like that, 68. Um, but this angle here, right? This angle or this angle here, that points north. So at my latitude, it was about 32 degrees or so. Um, this angle here from horizontal to there was like 32 and a quarter degrees. So that pointed north, and as you can see, the telescope itself was able to tip um, up and down. And then this whole thing, this whole orange thing, rotated left and right. And so, of course, one way is right ascension and the other way is declination. And it was all controlled by this little control panel here, which yeah, was just a bunch of buttons and dials um, and of course a computer. And you could type in the coordinates and you tell it to go, and the telescope goes.
You
Um,
ever play with the telescope or no?
did I ever what?
Play with the telescope or no?
Play with a telescope?
Yeah.
Well, yeah, I've told those stories a couple of times. They're um, the kind of work I was doing up there. Um, the sky had to be very, very stable, and but sometimes even when it was clear, the sky wasn't stable enough. The seeing was like really, really bad, and so it was on those nights where it was clear, but the seeing was bad, that I didn't have um, I couldn't actually collect data. So yeah, I had a blast up there. um, because they did have an eyepiece on this thing, and and uh, and so yeah, I got to look at all the nice things with a 61-inch telescope. So that was very very cool and very very fun. The only downside, of course, was that the seeing was really really bad. So, you know, when I looked at Saturn, um, and it filled, I think a couple of fields of view. Um, it was pretty yucky looking, right? But uh, the amount of detail that could still be seen was absolutely amazing because of all the light. Um, the 61-inch telescope, that's a huge huge light bucket, and so you're able to see faint things really really well. And so yeah, it was great. I saw right after they discovered Shoemaker-Levy 9, the that um, sort of series. Well, um, it was a single comet. It broke into a series of like 21 pieces, um, and strung themselves out like beads on a necklace. And I think in 1990, was it 94, 95, impacted Jupiter. And so that was absolutely fabulous. But I saw it uh, soon after it was discovered. I think in like 1993, 1994, I forget exactly. I want to say 93. And yeah, I mean, it looked like a cigar. It was just this very very elongated, um, fuzzy object, um, with a 61-inch and bad seeing. I I don't think that I could see like the individual pieces or anything, but I did actually see it. So that was very very cool. Looked at a lot of Messier objects, a lot of NGC objects, just anything I could think of, right? It's like, you know, it's clear I can't do my actual work. I have a 61-inch telescope. What am I going to do? So, yeah, that's a no-brainer. So, yeah, that was a lot of fun. And this scope is definitely still in operation. I'm happy to say this this is one of the telescopes that they were considering mothballing because it was so not used. And even at that time, I'm like, if you mothball this, then you're going to let me up here um, every night I want to, right? Because you know that's just crazy. So yeah, I'm really glad that it has another life now, um, because it's a awesome scope. It's really an awesome scope. Great great big toy. This is one of the reasons why I didn't get um, aperture fever, right? Because I had access to this, right? This monstrosity. You see how big that is? It's big. So yeah, aperture fever I never caught because uh, I found the cure, and there it is. I'm standing right next to it. Yeah, it was very very fun and very very cool. Amata actually got a paper published on it, um, which I think I don't know if it's I don't know if it's on archive.org or not. I don't think archive.org goes back. quite that far. Come on, archive. I don't know why it's going to the Daily Show. That's kind of weird. Come on. Poor machine. Let's see. It was called UBV photometry. Was it called Hot White Dwarf Stars? I don't remember. No, I can do it this way. Let's go over to ADS and we can search that way. Got to remember what the website URL is for ADS. ADS Harvard search. There it is. We'll get it here. Let's see. Here's all my publications, everything that I've participated in publishing. UBV photometry of hot white dwarf stars. There it is.
That's actually your paper?
Yeah, I was the author of this one. All the work I did on it, man, I better be the author of this paper. So there it is. So how many did I end up doing? I don't remember. Come on, zoom in. Don't remember how many I did. I'll tell you a story though about this paper, the writing of this paper. So of course I wrote it and sent it off. We had it published in the Astronomical Journal, right? And so, sent it in. It was accepted. They sent back a what's that called? It's like a draft, right? This is what it's going to look like in the journal. Make sure that there aren't any typos. Make sure that all the pictures you have are sort of in the right place. All of that, right? And we were all ready to give them, our final okay. And I read first sentence, and it did not read what it says here. There was one letter that wasn't supposed to be there. And that was this W was not a W, it was a T. So it said, with the advent of efficient CCD spectroscopy, it is not practical to determine reliable, effective temperatures and gravities. So that changes the whole thing, right? So last minute I caught that, and it's like, no, that needs to be now. So yeah, that was a scary thing. 84. So 84 objects I ended up measuring with pretty good accuracy and precision. But yeah, that was a fun project. I actually ended up building my own filters as well. The Johnson U, B, and V filters are actually combinations of two or more filters layered together. And so I went over to the Kit Peak optical shop and actually made the filters that I used in this thing. So yeah, it was very, very cool. Fun project for sure. For
So this
sure.
paper was made in '93, right?
93. Yeah, yeah. That's when it was published. So here's all the data, and these these uh, these errors are pretty valid. So pretty precise. We were getting down to hundredth of a magnitude precision on these measurements, so that's not too bad. But you know, uh, most of these objects were measured multiple times as well. So that's where it took a lot of the time, because I looked at these, uh, you know, 2, 3, 4, 5 times um, over the course of a couple years. So yeah, it was a fun project. It was fun. All right, well, cool. I was. Did I? I don't think I did. Don't think. I don't think I posted anything about M104. Okay, so Uncle Bill again was kind enough to post some some charts showing where Hoag's object is supposed to be in the sky. So yeah, it looks like it's over in Serpens. Is that what I saw in the chat? Or I saw somewhere. Don't remember exactly where I saw it. Where did I see that? I don't remember now. Anyway, I think this is Serpens. I remember right. Right next to Boides. Here's Arcturus. So cool. Corona Borealis up here. Oh, here's Serpens over here. What is this one? I don't know what constellation that is then. I don't know all my constellations. At least not the sort of the minor ones. Don't know those. Never did. Probably never will. All right. Well, cool. As I said, I wanted to look at M104 a little bit more, and I was actually doing that today. I was looking into it a little bit more, and yeah, it's a pretty amazing galaxy. It's kind of an unusual one. It's sort of like Hoag's, in that it's a little unusual because it's got sort of the look of an elliptical galaxy, yet it has this dark dust lane in it as well. So let's go back over here and see. So did it say how bright? Apparent magnitude? I don't see an apparent magnitude here. I see an absolute magnitude. Now, an absolute magnitude for a galaxy is a little strange. The absolute magnitude of an object is, now follow me on this. It's the apparent magnitude of an object if it were 10 parsecs away. Okay, so like in the case of our sun. Okay, if our sun was 10 parsecs away from us, then it would have um, um, an apparent magnitude of, I think, like about magnitude 5. Okay, so it would be sort of just barely visible, even in a dark sky. It would be one of those really faint stars up there, um, and that's at 10 parsecs. Okay, so um, so I can understand this for a star, right? The absolute magnitude of a star, because it's sort of a single object, and 10 parsecs is not very far, right? I mean, it's 32.6 light years away. That's like really close. Okay, so the problem I have with um, the absolute magnitude of a galaxy is that the size of a galaxy is tens of thousands, maybe hundreds of thousands of light years. So that, compared to 32 light years, is, it's just yeah, it it really doesn't make physical sense. So I'm not exactly sure how they arrive at that number. Um, I'm not exactly sure. It's sort of confusing. I have to look into that a little bit more. How they determine the absolute magnitude of a galaxy. Because, I mean, if the galaxy was that close to us, um, does that mean, is it like how far how far we are from the center of the galaxy, or how far we are from the edge of the galaxy? I don't know. Um, yeah, it's just very strange. Hope that makes sense. So here's M104 in the infrared, and you can see that gas and dust really sends out a lot of light in the infrared. So what you're seeing there is just warm gas and dust. Yeah, our instro, most of the time magnitudes are computed for like the entire area. So if you have an extended object like a comet, um, or a um, galaxy, it's sort of the combined magnitude of the whole thing. It's as if um, you piled up all that light onto a single point. That is the magnitude um, that they're talking about. So yeah, that's absolutely true. That a fifth magnitude comet is definitely not going to be as bright as a fifth magnitude star. No way. Because it's the combined brightness of the entire thing that makes it fifth magnitude. It'll always be fainter. So what part of the galaxy, tens of thousands of parsecs wide? Right. Exactly. I'm not quite sure how they measure that. It's I mean, you can calculate it, but it doesn't make any physical sense. So yeah, it's a bit of a weird concept. Yeah. All right, well, cool. Well, there's M104 in the infrared. I guess they were doing some radio observations of the nucleus of this galaxy, and found that it did have a jet going both north and south. And I think they were saying that the northern one. Let me see if I have it here. Uh, is this the one? So I'll post this in the Discord really quick, and then we can look at it. Let me make sure this is the right one. My poor machine is being line of sight velocity dispersions. That's not quite it. Is this it? Maybe this is the one. I was looking at a couple of papers about M104. Yeah, okay. This is am I going to change gears on you guys? Yeah, I'll change gears on you a little bit. Here's a paper. I'll post it over on the Discord so I can grab it on my laptop here. Let's see. Should be there. Discord is great for that. So this is a paper that is looking at the globular clusters in a few of those galaxies, including M104, aka NGC 4594. So they were able to actually pick out, I think, like 26 globular clusters they were able to identify and actually measure. See what it says about. Okay, so NGC 4594. So globular cluster ages between 10 and 15 billion years old. So that's pretty old. Especially since 15 billion years. That's actually older than the age of the universe, right? So. Let's see. Yeah, old. So they present these lists at the end, and they just did sort of basic photometry on these. They looked at them, I think, in 3 different colors. Let's see. There's 4472. Let's look at. Okay, here it is. So here's NGC 4594. So they looked at it in V, I, and K. So V is around 550 nanometers. I want to say it's around a micron. I think it's about 1,000 nanometers. And then K is, I believe, around 2.2 microns. So this is visible, and then this is infrared, and this is even more infrared. So, and these are the magnitudes that they found for each of these globular clusters. See, so here is the position of all of them. Yeah, it looks like they found 26 of them. And so here are the positions. As you can see, they're really close to one another, right? Makes sense. And they're all pretty darn faint, right? These are, 19.4, 21 and a quarter. That's really, really, really faint. Really faint. But pretty good precision, right? They're getting let's see, they're getting millimagnitude precision here, 8 millimagnitudes. So that's not bad, you know. Looks like they're usually good to about like 100th of a magnitude, which isn't bad. Here's one that's a little bit out, 10th of a magnitude off. Don't know why exactly, but yeah. So those are the globulars that they found in this galaxy. Pretty cool. And then what they can do is they can make these diagrams, these either color magnitude diagrams or color diagrams. So it's all they do to make these is they've got these three colors, right? V, I, and K. And they take V and subtract it from I. And then they take V and subtract it from K. And that's what makes what's called a color, right? It's just the difference in magnitudes. See, so V minus I versus V minus K. And that that's a Hertzsprung-Russell diagram um, type of thing that can actually show various populations. It can give you an idea about how old the stars are, all kinds of stuff. Um, you can get just by looking at the differences in colors. So very cool. They've got some theoretical lines here showing, you know, how old, um, you know, if this cluster was what 3 billion years old, say. Here, let's zoom in on. Oh, let's look at the right one. 4472. We're looking at 4594. So if these clusters were, say, 1 billion years old, then they would all sort of be on this line, right? Well, they're not. They're way up here, right? If the cluster was 3 billion years old, then they would all sort of lie along this line, right? Well, they're really not. They're leaning more towards 15 billion years old, which that's a little that's a little weird. That's a little strange, but yeah, there's a lot of uncertainty in these kinds of measurements, and yeah, it's hard to know exactly. But anyway, so yeah, a little bit more about M104. Looking at some globular clusters inside of it. The idea behind globular clusters, um, at least the theory is is that they formed about the same time that the galaxies did, and so they sort of contain the history of of um, the galaxy, and you know um, stars inside of those objects we think we have a pretty good understanding of. Uh, who knows if we really understand them or not? But we think we do. So we can actually use that information to sort of guess how old they are, and therefore how old the galaxy is. Um, and once you know how old the galaxy is, you can start making all kinds of guesses in terms of why it is the way that it is. So yeah, um, being able to see globular clusters is a really great way to sort of get a handle maybe on sort of the fundamentals of of um, of parameters of the galaxy, like how old it is, um, um, like how old it is. So very, very cool. All right, I think I'm going to get out of here for now. Now tomorrow at 0 hours UTC, right on the button, I'm going to be over on my Rabbit room, I guess. We're going to watch a pretty cool movie. It's called oh man, I'm gonna mess it up. Uh, where did I put it here? If I look at it, I can pronounce it. Otherwise, I can't. Where did I put it? Yeah. So, Koyaanisqatsi. It's it came out, I think in the late '70s or early '80s or so. Francis Ford Coppola um, produced it, and Philip Glass did all the music. And if you haven't seen this film, um, it's it it's pretty interesting. Bobby, have you seen this before?
No, but I don't. I'm not going to be here for the Rabbit stream or
Okay,
the ADL stream because we're going to be on a viewing party for a WWE pay per view.
that's right. That's right. You mentioned that. Well, it's definitely, if you haven't seen it, um, give it a look. It's on YouTube. It's divided into parts, right? So 10-minute segments. There are eight 10-minute segments, and then the last segment, the ninth one, is like 5.5 minutes long or 6 minutes long or so. So it's almost a 90-minute long uh, movie, but I'm well not going to give it away at all. It's just extremely interesting, and so I hope you like it. And yeah, so that's what I'll be playing tomorrow at 0 hours UTC. Um, so yeah, make sure to subscribe to my Rabbit channel, I guess you call it, and um, if you're
And
there,
subscribe to mine because I might be able to do whatever I want.
yeah, yeah, very, very cool. Yeah, make sure subscribe to Bobby's as well. He's doing some good stuff too. It was really, really, really awesome to listen to Steve Roach yesterday. He's uh, he is definitely, I would say, in my top five for sure. For sure, he's absolutely amazing, amazing. All right, so I'm gonna get out of here for now.
Hey,
Um,
Cos, you're gonna be up because I might do some Hearts of Space.
okay. Am I gonna be up? Yeah, I'm probably gonna be up. So yeah, yeah. I'll grab some more chocolate and listen in.
And I wonder if Adelana and Patrick's gonna come as well since I got them as friends.
Yeah, you know, all you can do is an invite, and you know, as I say, I can say yes or I can say no. So that's all you can really expect. So yeah, yeah, I definitely am probably going to say yes. I'll give a listen for a little while at least. All right, but I'm going to get out of here for now. I'm going to end this live stream. We'll see you again in a little less than 23 hours or so, just a little less than one complete rotation of the Earth. So it's it's really amazing how fast we're moving, um, and we don't even know it. We don't even know it. can't really even tell unless you sort of look around a little bit. And it's like, oh, the sky is moving. Okay, I get it. All right, I'm going to get out of here. Take care. Thanks for everybody in the chat. I will see you again tomorrow, 2 hours UTC. Bye.